Next up, we have Yi Sun.
Great. So the title of my talk is Data Augmentation as Stochastic Optimization, and this is joint work with Boris Heinen from Princeton. Okay, so let's recall that data augmentation is the procedure of replacing your data set with an augmented version of the data set at each step of training. So for example, if you look at the images below, one might apply some small geometric transformations, some color jitter, or add some noise during training. And the empirical outcome that we've seen is that pretty heavy data augmentation improves the performance of large models in many different domains, including vision, NLP, and voice. So if we think about what data augmentation is doing, there's two types of things which come up. The first is augmentations like horizontal reflections, small geometric transformations, and time translations appear to leverage sort of approximate invariances in the data distribution to expand the span of the training data. And a second class of optimizations, augmentations, such as additive noise or random projections, seem to inject noise into the optimization procedure, and there's the belief that this will regularize the optimization trajectory. So while these intuitions are pretty well established empirically, when we actually decide how to augment for a specific training problem, our task is a little bit different. What we want to do is to first compare different augmentations and evaluate them so we can choose which ones to use. And once we've chosen the specific augmentations we want to use, we want to schedule the learning rate and augmentation strength so that we can converge to a good optimum. So in this talk, I'll give a theoretical treatment of these questions in a very simple model. So we're going to leverage a connection between data augmentation and a stochastic optimization procedure. So let's consider the minimization of a certain empirical risk function. So here I'll take a data set D consisting of some input-output pairs X and Y. And all I'm going to do is just minimize the sum of some per sample losses with respect to some model F depending on weights W. So in this context, I want to view data augmentation as the process of replacing my data set D with a usually random augmentation D sub t at each step t. And then I'll run gradient descent on this augmented loss. And so what I'll find is I'll get updates which are given by the gradient of this augmented loss. And I want to view those gradients as stochastic gradients of what we call the proxy loss, namely the expectation over the randomness of the augmentation procedure of this augmented loss. So from this perspective, a step of augmented gradient descent is simply a single step of some stochastic optimization algorithm for minimization of the proxy loss. So to make this a bit more concrete, I want to specialize to the setting of overparametrized linear regression for the rest of the talk. So here, our data set consists of input and output matrices X and Y, whose columns have individual data points. I want to take the overparametrized setting where the input dimension is greater than the number of data points. And I'll just consider linear regression using the mean squared loss. And so that means that our original loss is simply the squared Frobenius norm of the residuals. So to give a few examples, if I take additive Gaussian noise, I simply take the data set, the augmented data set at step t to be a perturbation of the original inputs by IID Gaussian noise. And some easy computations reveal that in this case, the proxy loss simply adds an L2 regularization term to the original loss. A second example, which illustrates how general this framework is that stochastic gradient descent, although it's not generally considered a data augmentation, also fits into this framework. Namely, we can consider the augmented inputs and outputs X sub t and Y sub t to simply be right multiplications of the input data matrices by a matrix A sub t, which selects data points for this batch. And in this case, the proxy loss is simply a weighted L2 norm of the residual. So let me now go deeper into Gaussian data augmentation and see what we can say about it using this connection. So let's remember that the proxy loss is simply some L2 regularized loss. When we run gradient descent for linear regression, it's useful to decompose the weight matrix into two components. One, the parallel component, which lies in the column span of XX transpose, and one, the orthogonal component, which does not. So the original loss has minimum norm optimum, which lies in this column span and can be written explicitly in terms of the data matrices. Here, the plus denotes the Moore-Penrose pseudo-inverse. So if we don't augment our data, we find that normal gradient descent only modifies the weight matrix in this parallel component, and therefore it converges to the minimizer of the loss shown at the bottom of the slide. Namely, it's this minimum norm optimum plus the orthogonal component of the initialization. So this optimum has the good property that it minimizes the original loss, but it has the bad property that it does not modify this orthogonal component. On the other hand, if we take a positive augmentation strength, sigma sub t, and fix it for L2, then we're just doing ridge regression. And in this case, the L2 regularization will, for good values of the learning rate and augmentation strength, drive this orthogonal component to 0. And in this case, the proxy loss has a unique minimizer, which is given by the ridge optimum. So we'll notice that in this case, we've killed the perpendicular component, but unfortunately, our regularization introduces some error which does not minimize the unaugmented loss. On the other hand, if we take the weak regularization limit of these ridge optimizers, namely if we take the limit sigma goes to 0, we see that it actually converges to the minimum norm optimizer. And so this suggests the question of whether we can actually produce some augmentation schedule which converges to this minimum norm optimum via a joint schedule on learning rates and augmentation strength. So if we specialize our general results to Gaussian data augmentation, we show that we give conditions under which this is the case. Namely, if the augmentation strength and learning rate both converge to 0, and for technical reasons, we want the augmentation strength to be decreasing, then we show that under these two conditions, for any initialization, we actually converge to this minimum norm optimum. And we can actually give some rates for this as well. So just to comment a little bit on the two conditions, the first condition, that the product of the learning rate and augmentation strength should have divergent sum, that's required to ensure that the optimization trajectory moves enough in the orthogonal component to kill it. The second condition, that the square of the learning rate times the augmentation strength should have bounded sum, well, so the summand is proportional to the gradient noise that's injected at each step of optimization. So that second condition is roughly equivalent to the fact that the amount of noise injected in the gradients is finite. So this result is a special case of a general result, which applies for any type of augmentation in this very simple overparametrized linear regression setting. So let me tell you about it. So in this case, we replace this ridge optimizer by the minimum norm optimum of the proxy loss at step t. It also has an explicit form, and it involves only the second moments of the augmented data matrices. So here it's explicitly the second moment of y x transpose, or the mixed moment of y and x transpose, times the Moore-Penrose pseudo-inverse of the second moment of x. And our general result says that if the learning rate converges to 0, under the condition that, for simplicity, that this second moment has full column rank, then we need the following three conditions to ensure that the weight matrix always converges to the t goes to infinity limit of these minimum norm optimums. That's going to be the analog of the weak regularization limit of ridge optimum. So let's break down these conditions a little bit The first condition again ensures roughly that we have convergence in the orthogonal component. And the third condition, again, is an upper bound for the total gradient noise. So together, these two conditions are reminiscent of the classical conditions of Monroe and Robbins for convergence of stochastic optimization of a static objective. In our setting, the objective, or the proxy loss, is not static because we're allowed to schedule the augmentation. And this causes us to introduce the second condition, namely that the minimum norm optimas at each step cannot move too fast. If these move too fast, then maybe our single step per proxy loss would not move fast enough to converge to their limit. Okay, so with these three conditions, we get a time-varying analog of the classical Monroe-Robbins condition, which handles any augmentation, but in this restrictive linear regression setting. And we also have analogs of this result, which give and handle general second moments. Finally, to close, I want to illustrate that this framework also is general enough to encompass stochastic gradient descent pretty uniformly. So let's recall how to put SGD into our framework. So if we pick a batch size B, then SGD simply takes the original data matrices X and Y and right multiplies them by some batch selection matrices A sub T. So if we want to do sampling with replacement, then A sub T would simply be the matrices whose columns have a single non-zero entry that's randomly chosen to be equal to 1. In this setting, the proxy loss is the same as the unaugmented loss. And we also find that SGD only modifies the weights in the parallel direction. So specializing our general result to this case shows the following. Suppose our learning rate converges to 0 and its sum diverges. Then, as expected, for any initialization, we converge to the minimum norm optimizer plus the original orthogonal component. That's the same as for gradient descent. On the other hand, we're also able to get rates for SGD. Namely, if we know the rate of decay of the learning rate, then we can get an exponential rate of convergence to this optimizer. Now, these results are known using sort of SGD-specific methods, but this illustrates that our method is general enough to cover both Gaussian noise and SGD uniformly. Okay, so to summarize, we presented a framework which can handle completely general augmentations in this pretty restrictive setting of overparametrized regression. And there are a few natural extensions to study. First, we've only really discussed noising augmentations so far, whether through the choice of data points or through directly adding noise to the inputs. So there are a few other common genres of augmentations, such as label-preserving transforms or mixing augmentations. And it'd be interesting to see what the specializations of our conditions in the general results mean for these types of augmentations. Secondly, obviously, most models in practice are nonlinear. So one might ask what the relevance of this linear regression setting is. Well, one answer would be that for a nonlinear feature model, augmentations in input space, once passed through the feature map, simply correspond to some different augmentations in feature space. So one can translate our main result for fixed nonlinear feature models to a result for those simply by passing through the input augmentation through the feature map to feature space. So you can check out our paper on arXiv at the URL below, and I'm happy to take some questions.
Thank you very much. That was excellent. Do we have any questions? I don't see any in the Q&A. Are there any panelists that would like to ask some questions? If not, I was curious as to, I don't think I caught this detail, but the range of distributions on the augmentation noise that you account for in this particular model, how general are they? I just don't think I caught that detail.
They're actually basically completely general. Well, what our result shows is that all that matters is, roughly speaking, the second moments of the augmentation, the second and perhaps fourth moments of the augmentation. So if you look at the conditions in our general theorem, they really only involve expectations of norms involving up to 4 of the augmented matrices. So anything where you can control those can be handled by this theorem.
Excellent, thanks. We have one question from Cameron Harris. Can you see that question? I'll just read it out for everyone. Do you think that more complicated augmentations like reflections of images all end up leading to a different proxy loss? Any thoughts about what this would look like?
That's a great question. So I think this plays into the difference between augmentations which take advantage of some invariance in the data versus augmentations which seem to only add noise. So in the case of reflections of images, one might believe that the second moment of the data doesn't really encompass the full, doesn't have column span fully encompassing the full span of perhaps the true data distribution. So one might want to basically synthetically expand the data distribution by applying a reflection to all of the data, taking that combined data set, and then treating this augmentation as sort of randomly subsampling, basically some form of batch selection. And so we expect actually the convergence rates to be a bit different for that type of augmentation versus this type of noising augmentation.
Great, thank you. Any other questions from the panelists? All right, well, thank you again. Appreciate it.